Hi and welcome. My name is Torbjörn Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Cheng Kung University in Tainan, Taiwan. I'm also the general chair of this workshop. Now, the sculpture next to me is called Endure or People in Grief and was created by Zhou Lianxi, who got his degree from the Department of Mechanical Engineering, and then he did a master's degree at New York University. After his retirement, he studied art and created this sculpture, which he donated to the department and now is placed next to our department. Now it's my pleasure to introduce our honorary chair, Chair Professor Wu, who will give his welcome address.
It is a pleasure to welcome all of you on behalf of the National Cheng Kung University in Taiwan. I am proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OD camera together.
Hello and welcome. I am Akram Ashiani, postdoc researcher at the Department of Mechanical Engineering of National Cheng Kung University in Taiwan and assisting chair of this workshop. It is my honor to introduce Mr. Jose Ramon Chang Arias, who is a PhD student in the Nordling lab in National Cheng Kung University in Taiwan. He has been a visiting researcher in the Center for Applied Intelligent Systems Research at Halmstad University in Sweden. His research interests are artificial intelligence and deep learning. He will present facial feature point detection using deep feature encodings to propose a pipeline for feature tracking to identify the most salient crops in an image and match them to a second image. The result shows that their method creates better feature descriptors for image registration than the traditional algorithm.
Okay. So welcome everybody to my talk on facial feature point detection using deep feature encodings. My name is Jose Ramon Chang. I am a PhD student here at the Nordling lab. I have been working on deep learning for roughly 5 years. And I've also had the chance to work as a researcher in Sweden, in Halmstad University, in the Center for Applied Intelligent Systems Research. I would like to start my talk by thanking Dr. Nordling, Dr. Ashiani, and Dr. Wu for their kind introduction. And I would also like to preface the talk by telling you that this is a little bit technical paper. So I will try my best to explain it in the time that we have, which is roughly 45 minutes. If you have any questions, please feel free to ask them because I think in the end we're going to have a Q&A session. But let me show you what I have for you today. So let's start with the outline. So as you might know, this is the paper of my PhD topic. So I will discuss a lot of and I'm developing this new method for feature tracking. So I'm going to explain what is it required for my method. So the training data set, we're going to explain the validation data set. Then we're going to go into different key points that are related with my methods, and then show some results and the conclusions that we can get after doing all of these things, right? So in my lab, well, typically when you ask a researcher to explain their project, they usually end up giving this convoluted and very long answer. So in my lab, we have, by tradition, designed this why, what, how figure. This figure is meant to be so that it's meant to be used so that you can explain your project in a very simple manner, right? So let me start by explaining the why part. If I can maybe make my thing a pointer. Okay, so the why part is that we want from videos, we want to quantify the heart rate, right? That's the main idea of our project. So right now, the way that you will know your heart rate is that the doctor will need to have a stethoscope, right, and put it on your heart, or there is a photoplethysmography item that you will put in your finger. I think that's what they use in the hospital right now. And then based on the color changes of your blood, then you will, check what is your heart rate. So we want to do it remotely, right? Just through the video, and we're going to do that through something that is called imaging ballistocardiography. So this basically refers to the process that when your heart pumps blood, um, there's and you're standing still, there's this subtle movement that is happening because there's blood flowing through this carotid artery that makes your head bump up and down, right? And then we want to track your head or features in your face to be able to, while we track the features in your face, being able to at the same time quantify your heart rate. Another big reason why we want to do that is because we want to avoid using sensors on your body. Our principal investigator, Dr. Nordling, came up with the inspiration for this project when he had his son born, and he realized that because babies, you can put a stethoscope on a baby, right? The baby wouldn't stand still, and the stethoscope is cold. So in addition, you cannot put this photoplethysmography sensor in their finger because the baby is moving like crazy, right? So they have to like stick some sensors to the skin, and those sensors can harm the skin of the newborn baby, which he has a very sensitive skin, right? So that's the idea, is to avoid all of these sensors and then do the quantification of the heart rate remotely. So the what part is that what are we doing is that we look at the video, right? A video is a collection of images. So let's say that I have the first frame, right? And then in the first frame, I have several things that I could track. Like, for example, I could track an eye, like more realistically, it would be the corner of an eye, or the corner of my mouth, or maybe a mole. And then the idea is that I will get that one, and then I will start comparing it with, in the other frame, right? To check where is that, like, which is the most similar feature and the most similar feature would be in there's a match, and then that means that on image B, on the next frame, my feature is located there. So now the how do we do it is the interesting part. It is what I love to do, and is what I come to do here every day. The how we do it is that we use an encoder part of a stack convolutional 3D autoencoder to be able to represent these features in a lower dimensional space. So we will get, for example, let's say that I have my first frame here, and then I will take that. Let's say I want to track an eye, right? And then I will pass that through my convolutional, to the encoder part of my stack convolutional autoencoder, and then I will get a feature vector, right? So I'll get like just a set of numbers that describe my eye in this case. And then in the second image, I will have several candidate things that I could track, like a mole, another eye, right? And then the idea is that I will pass all of this through the same encoder subnetwork, and that will give me different encoding representations of my feature, right? And the idea is that we want to match which of these encoded representations are the most similar, right? We want which of these encoded representation minimize a distance function. In this case, it will be, this eye, right? Because they're represented by having the same shade of blue. So robust matching of points between images is crucial for developing reliable tracking algorithms. That is because tracking algorithms tend to diverge once the matching fails above an acceptable threshold. Like if I'm starting to track an item on a video, right? And then suddenly, let's say I'm tracking the corner of my eye, and then suddenly, and it's tracking very good, but then suddenly it starts to track the other corner, right? Because maybe some frame, it is blurry or something like that. and then I could not see my eye. So then I start tracking the other corner of my eye. Then from that frame onwards, what I'm gonna be tracking is the other eye, right? And that's not good, because I always want to be tracking uh, the feature that I intended to track. And now the problem with that is that current state-of-the-art methods are notorious for not being reliable enough, and they require a set of conditions for proper functioning. Like, for example, like all the motion need to be the same on the surrounding pixels, or you need to have no photometric changes, so the light cannot change very bright. The some methods require the motion to be very smooth. So they're known to be not good in most situations, or they require, for example, also to have a corner feature, right? But yet they're still considered state of the art. So that's the gap that we believe that we can fill in using deep learning, because as we will see in a moment, these state of the art methods are actually they have been considered state of the art for quite a long time, and there has been a relative not a significant amount of improvement on them. These state of the art methods are namely speeded up robust features. We also have Scale Invariant Feature Transform. For those of you who are from the computer vision field, you will recognize all of these terms. We have the Lucas-Kanade term, and we have our deep encodings, or deep feature encodings, as we like to call it. So here, basically, we have a result for our tracking for a tracking in our validation dataset, and we have a video that is 169 frames, and then we have sorted the errors here, right? And you can see that our method, this orange line, never, I mean, it went above this 99% confidence threshold, which we define as a acceptable error, only for 1 or 2 frames. But all the other methods were above this threshold many more times than our method. That means that our method is much more precise to track features, at least on the skin, or at least the features that we track, than all of these other methods. Now, it's worth noticing that here we have a accessing log scale, and even our largest method, our largest error is roughly, say, what, 2 or 3 pixels here. While, for example, even Lucas-Kanade, which is considered to be one of the best methods out there, when it has its worst error is more than 100 pixels, right? So you can see that that's the big difference between our method and all of these state-of-the-art methods, that even when our method performs the worst, it's still under an acceptable error range, right? Like you will never find that you will start tracking something in your, if you're tracking something in your eye, you will never start tracking something in your hair or maybe in your chin, right? You always start tracking something like around that same area. So our pipeline is just more precise for feature tracking than the traditional computer vision methods under the conditions of interest for applications. And the success of our pipeline can be attributed to 3 main things. The first thing is learning of complex features through hierarchical feature learning, which is that's because we have a deep learning model. So the deep learning model is able to learn these higher level features from the original features, and these features are meant to separate the samples in the dataset. Then we have the preservation of spatial information, because we have applied a convolutional deep neural network. I mean, it's a convolutional deep stack autoencoder, which uses the convolution operation to look at pixels as a group. And then because it is an autoencoder, the latent space variables, or the space at the lowest compression or at the highest compression, is meant to capture the variance for regions within the phase area. And that's also because we have trained this autoencoder on a lot of different faces, so that it can recognize all different kind of eyes, all different kind of skin tones, all different kinds of eyebrows, teeth, nose, everything, you name it, it will be able to recognize it. And then here is just a table that summarizes our results. So you can see that for the 5 conditions that we tested our algorithm, we were superior in 4 of them. And when we were not superior in the ones that we were not superior, which Lucas-Kanade was the best, we were third after SIFT still, but you can see that all of them have a pretty good performance with just having two errors of 2 pixels in difference, right? So yeah, that's our method. So let me just briefly go through the introduction and the other stuff. So we define um, so feature tracking is interesting thanks to computer vision because there are many other applications that stem from it. Like for example, you could determine the the emotion of a subject, right? If for example, if the subject grins and you're tracking the corner of the mouth, then you realize, oh, this subject is grinning, so this subject is probably happy. Or for example, if the subject frowns, there must be some movement in the eyebrows like this, right? So you could determine that if he's feeling sad. You could determine, for example, the level of drowsiness of a driver. Like let's say if you have a camera on a truck and then you see the driver is moving his head like this, then you can determine that he's tired or he's drowsy. There are many different applications for it. uh, well, right now the one that comes to my mind is probably the filters in IG or Snapchat. Like, like there are filters that, for example, replace the color of your iris, right? With instead of replace the original color with, let's say, what, green, right? So for that, then you need to be tracking your iris all the time. So it is an important task to research. Um, so right now we define feature tracking as feature tracking as iterative image registration across multiple frames of a video, replacing the interest point at each step. So if I have my reference point, I get my first frame, right, and then I detect my reference. I pick a reference point there. Then I find that point on the second image. So the point that I find on my second image is now my reference point, and now I'm tracking that point in my third image. Once I find it, then okay, then I'm finding that point in my fourth image, and so on and so forth, right? So here I have just an example of feature matching using SIFT. So feature matching, like I said before, is basically if I have a lot of points in image A, these are candidate key points determined by the scale space extrema in SIFT, or Scale Invariant Feature Transform. For those of you who are not familiar with the computer vision terms, then okay, for these points, where are these points on the image B, right? So this is the, let's say I have a video of me blinking. So then, for example, you can see that this point is matched with this point here. This point here is matched with this point here, and this point here is matched with this point here. And not the thing is that not all the candidate key points have a pair, right? So you can see that there's, for example, because I'm blinking, the most obvious one are the ones in my eyes. So there needs to these points, the pair of points need to fulfill a certain condition in order for you to label them as a pair, right? And we'll talk about that a little bit more in detail later. So traditional image registration techniques basically can be divided into two. So the first is feature based, which aim to represent the image features into a high dimensional vector. Typically is 128 for SIFT, 128 dimensions for SIFT, and 64 dimensions for SURF, or speed up robust features. And then intensity based. So intensity based just aims to solve the optical flow equations. In other words, like where is the pixel moving, just based on the local pixel differences between each frame. And as I mentioned before, these are notorious for failing even when there is a affine local transformation, which is an approximation of perspective transform, or illumination changes, right? So illumination changes is the photometric changes that I was talking about, where you can have the light blinking or something like that. So so now we're gonna get into the little bit more technical part. I'm just going to, so for this, I'm gonna go through SIFT, SURF, and Lucas-Kanade right now, but just in a very quick fashion, because the main point of our talk is the deep feature encoding methods, the method that we developed. So for SIFT, basically SIFT, the first thing that it does is to find candidate key points, and it does it through blurring the image with Gaussian kernels of different sigma, so of different standard deviations. So then it will subtract these Gaussian kernels and get this difference of Gaussians. So this difference of Gaussians basically aim to represent the image at different scales. And then once you have this difference of Gaussians, you will have like this cake, this in this case it will be a 3-layer cake, right? Imagine that this is on the bottom, and this is on the middle, and this is on the top, and then you would aim to find the local extrema in this cake. So, and the extrema is defined by its 26 neighborhood. So it would detect either the maxima or the minima points in the 26 neighborhood. So in reality, SIFT blurs the image with many more different kernels and with different scales. But this is just a simplified example, so to understand what is happening. So once you do that, once you find this scale space extrema, then you will have what you call the candidate key points. So this is just so it will go by octaves, right? And then you will resize the image as you go up in the octaves. And then once you do that, then the next step, it will be to calculate the magnitude and orientations of the gradients around each key point. So to put it in simple terms, you will look at each key point, you will look at each red dot, and then you look at basically the stuff that is around that point, and you will, based on the stuff that is around that point, the stuff here, I mean, like the difference in the pixels, right? That's the gradients of the image. And then once you have that, then you can construct this feature descriptor. There is 128 feature dimensional. So you, for example, you have this point, right? And then you will weigh the surrounding pixels using a Gaussian kernel. So basically, the pixels that are closer to this point are more important than the pixels farther away. And then you will calculate the dominant orientation of each point, and then you will just create a histogram of these orientations, and then you would just using those histograms, you would just concatenate them to get this 128 feature descriptor. So SIFT is a very complex algorithm, but if you are interested in that, you can either look at my publication when it comes out in a couple of weeks, or you're welcome to also check the original publication. So now SIRFT is speeded up robust features. So SIRFT is an algorithm that is largely based on SIFT, but it was meant to be just more computationally cheap than SIFT at a cost of lower accuracy. Now, SIRFT, what it does is that we saw that SIFT obtain scale invariance using the Laplacians of Gaussians. So it's defined by this. So now SIRFT, instead of doing that, SIRFT uses box filters to approximate the Laplacian of Gaussians. So for example, if I have my original image is like this, right? And then I apply a Laplacian of Gaussian in the y direction twice, then I will get something like this. And if I get in the box filter in the y direction, would be something like this. So you can see how it kind of looks like the same, but not really. So that's the cost of approximating this function with the box filters. And then you can see the same thing, like if I do this and I apply first in x and then in y, then I will get something like this. And then you can see how the box filter kind of gives you the same answer, right? And then we have similar cases for the other stuff. So this second column should be compared with this should be compared together with this fourth column. And now SIRFT, to put it in simple words, so how does SIRFT implement scale spaces? So SIRFT uses different sizes of box filters to approximate different scale spaces, instead of using instead of using Gaussian kernels of different sigmas, as it was demonstrated in SIFT. and then the descriptors of SIRF is just a vector that contains the sum of the hard responses around the key point. So if this is our key point, then I'm going to find the dominant orientation of my key point, and then I'm gonna calculate the hard responses of the relative x and y direction, and this relative to my dominant orientation of my key point, and I'm just gonna concatenate those into a vector that is 64 dimensional. So it's gonna calculate the hard responses in x, the sum of the hard responses in y, and then the sum of the absolute responses in x and the sum of the absolute responses in y. So in other words, is SIRF also aims to, so the hard responses like SIFT, the process of creating descriptors with SIRF is just to look at the stuff around the key point, right? Look at the gradients of the key point. Look at the, how does the surrounding area of around that key point look like, and then you try to describe it using a vector, right? Okay, so lastly, Lucas-Kanade. I think I have been spending more time than I would like here. So Lucas-Kanade just aims to solve this equation. So this is the optical flow equation. So this is the intensity of the change in the changes in intensity as a function of time. This is the gradients of the intensity times the velocity vector. So this basically just can be represented as this equation as A V equals B, where A in this case now becomes the spatial gradients of the point. So it will be the intensity of the points in the partial derivative in respect to x, and then the partial derivative of the intensity with respect to y. For that, for a window of points around the point of interest, and then that's gonna be times the flow vector that contains the velocity, which is the changes in the position, and that's gonna be the temporal. That's gonna equal to, so it will be just putting this term to the other side of the equal sign. That's gonna be equal to the changes in the intensity as a function of time. So this system is usually overdetermined because here the only two unknowns that we have is these two, right? We want to find the changes in x and changes in y to be able to determine, okay, this pixel moved 3 pixels to the left and 1 down, something like that, right? So the only two unknowns is this, but in here we usually have a usually have a window that is more than 2 pixels. So for example, I could choose a window that is 3 by 3, like a 3 by 3 window around the point, and that will give me nine points that I could work with. A 5 times 5 window will give me 25 points, and that makes the system overdetermined. So then Lucas-Kanade uses the least square to find a solution to the V, right? The V is the one that we care about. So of course, here this method is considered to be one of the most robust methods and the most accurate methods, but it also comes with a lot of assumptions that need to be fulfilled in order for it to work properly. So for example, one of the assumptions is that there cannot be photometric changes, so there cannot be like a large illumination changes from this method. In the picture, there needs to be a small motion, and then the neighboring pixels should have, the pixels inside that window should have similar motion, right? In order for it to determine accurately where is it moving. In addition, you need to pick. It is very important to pick a corner point, so that you can avoid the aperture problem. Okay, so then we go into, okay, how have people have how have people been trying to solve this tracking problem using deep learning? When we did a literature review on this topic, we realized that most of the people, when they do tracking, they use this tracking paradigm, which is tracking by detection. in which you first use a neural network to detect the object, and then uh, you use this algorithm that just basically aims to match the same object across two images, right? Now, and most of the research in this part is on developing this tracking, this associating algorithm to match the same. For example, if in the image you find two people, and then on the next image you find the same two people, but just with some difference in their position, then you want to find where a person A in from image A that's on the same person A on image B, right? So you can match the two things. But if we look at what have, for example, these studies having tracking, you can see that they use different state-of-the-art methods for detecting. So they use, for example, faster RCNN, or they use single shot detector, or YOLO. Uh, but the main problem is that they aim to track pedestrians, athletes. This guy was looking at pigs. This guy was looking at cars. So what they are looking at is larger objects, right? We are looking at features in a face, like for example a mole. So our problem is inherently much more difficult than their problem, due to the fact that we are tracking stuff with that is just smaller, right? Uh, 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 in my opinion, finding a mole in a face is much harder than finding a whole person in a street, right? Because a person has much more distinct features that could differentiate him from the environment, right? Okay, so our objective is to create a pipeline for feature tracking that uses a convolutional stack autoencoder that has the following features. So the first is that it's completely unsupervised neural network training. So we don't, the novel thing about our algorithm is that since most of the uh, learning strategies are supervised, so they require you to, in addition of the image, in this case it will be to tell the algorithm where is the let's say, where is the nose, where is the ear, where is the eye. In our case, we don't tell the algorithm this stuff because it's unsupervised. So the algorithm just looks at the face, and then you will be able to detect stuff just from looking at the pictures itself. It should be able to identify the most salient crops in an image. It should have a convex distance function of the neighboring points. And in addition, our autoencoder must be invariant to skin, hair color, facial expression, background color, illumination, reflections and shadows, scale, invariant, and variant to rotations. Yeah, so this is so that we can basically use this autoencoder on anybody, right? Independent of their race, independent of where they are, independent of their age, independent of whether they're happy, sad. We would like to still be able to use this autoencoder to track stuff on their face. Okay, so the data set. So let me just go through this. So this is the training data set for a model. So in here, I want to introduce as much variance as possible to my model, so that my model has seen all different kinds of faces and is able to deal with all kinds of these situations, right? So the data set that we use is this University of Tennessee Knoxville face, which is a large scale face data set with images collected from the internet. It consists of roughly 24,000 images of faces in the wild. So these are just some examples of the faces that you can find in this data set. So you can see that we can have faces of very young people and very old people at the same time. We have faces with different angles of the camera, different uh, uh, facial expressions, different. Well, some people have glasses, right? But the faces are usually looking at the screen, right? So the faces are labeled by age, gender, and ethnicity, and then the ground truth of the age, gender, and ethnicity and race are estimated to this algorithm that is called deep expectation, but then they are double checked by a human annotator. And then here we can see a distribution of the ages of the samples in our data set. So we can see that basically, yeah, so there's a lot of people with around 30 years old, but for the most part, it seems to, be reasonable because as we go older, right, there are probably, yes, less pictures of older people. Uh, then we have roughly the same proportion of male and female, the same ratio, and then we have roughly 40 this distribution of the races. So it's mainly white, but it also contains black, Asian, Indian, and other races. Like other races correspond to Hispanic, Latino, and Middle Eastern. Okay, so now this data set contains stuff that is not phased, right? So that's not good for our algorithm because it just introduces noise to our algorithm. So what we do is that we use this OpenCV ResNet 10 model to detect the phase on each of these pictures, and then this is the data that we use to create crops to train our algorithm. So basically, if I have this picture of this baby, I will use, after I run the face detection model, I will get this face, and then I will use these faces to create to create the data for my algorithm. Okay. So here we have so here we have just the histogram of the areas and aspect ratios of the faces. So they seem to follow this bell curve, which is good. Okay, so how do I create crops to feed to my deep autoencoder? Well, I want to create my autoencoder um, to be able to reconstruct face crops, right? So I need to feed it face crops in order to do that. So I will start with an image, right? And then let's say I start picking up this corner part, which size of 31 times 31 pixels, and then I will crop that, and then I will move my window without overlapping. The stripe will be the same as the window length, and then I will go into the next position and I will crop that part, and then I will keep going until I eventually go throughout the whole image, and then I will do that for every image that I have. So that will give me roughly 2 million training images for my autoencoder. So yeah, so this basically means that I have a lot of data to train the autoencoder, and this data has a lot of variety, which is exactly what I want to be able to train this autoencoder that can generalize to any previously unseen situation. Okay, so the validation dataset. So basically, we tested our algorithm in two different datasets. So this data that we have is from our in-house dataset, and there are videos that are coded at 50 frames per second at 180p and coded in the RGB color space. So the first one is the remote ballistocardiography one. So here, basically, it's a set of two videos, where the first video is the small, or in other words, static motion, where the subject is instructed to just stand straight, right? Stand still in front of the camera, and then just look at the camera for a couple of seconds or a couple of minutes. Then the next one is the bike motion. So in the bike motion, the subject is moving uh, periodically because the subject is riding a bicycle, right? And then the last one is, well, for the last one, we kind of wanted to see, like, okay, can our method generalize, because our method has been seeing skin a lot, right? I mean, the face crops is basically just crops of skin as well, right? And can I, for example, use the same model that I train on faces to detect stuff on skin? And that's why we decided to introduce this dataset, which is the Parkinson's disease postural tremor test. So in here, the subject is just basically having his hand here, and for those of you who are not familiar with Parkinson's disease, this posterior tremor test is just like you basically tell the subject to stand still, but the subject, because it has Parkinson's disease, right, it will inevitably uh, move. and shake, right? So yeah, so this is just the videos that we have. So this is the static one, this is the bike one, and this is the postural tremor one. And then you can see how the motion is different for all of them, right? Okay, and we just crop these ones and resize them to 420 times 300 pixels, and subsample them to 2 FPS to shorten the computation time. So here I have these are the features that I selected to track. So for the static one, I selected to track this face mold that I have on my face, and also my nose tip. And on the bike video, I selected to track the same thing, the same face mold and the nose tip. So here we just have the enlarged version. And for the Parkinson disease posterior tremor test, I have selected to track this mole in his hand. So these squares are 31 times 31, and this is gonna be fed. This is the ones that this is the stuff that I'm going to encode using my autoencoder. Okay, so I resized it to 420 times 300 because if we look at the distribution of the areas and aspect ratios, we can see that basically these fall roughly in the middle, right, of the curve, which basically means that it's also like a good size. It's not neither too small, neither too big, so that the model will be able to deal with it very well. Okay, so the methods. So this is the figure of an overview of my methods. So this figure is actually quite interesting. And let me go through it very quickly. But basically, everything starts with the data, right? Our training data set is used to train our convolutional autoencoder. Then using this autoencoder, I will get the encoding part of it and this will be part of my tracking methods. And then the other stuff would just be used for the other three methods that I'm using to compare. So Lucas-Kanade, SIFT, and SURF. And I've also labeled all of the pictures my face mold, for example, my nose, and in the Parkinson one I have labeled the hand mold. So now once this validation dataset comes through these methods, then some of these methods give me pixel level prediction. So in other words, they give me the position of the feature like in an integer level, right? And Lucas-Kanade gives me the position as a floating point. So Lucas-Kanade has this inherent advantage because, as you can see, in some cases the methods are all very good. So it is very hard to distinguish which one is better than the other one if these three are at pixel level prediction, right? So then we have designed this sub-pixel level prediction part. So to give me the prediction on in a floating point. Then once I have all my predictions in a floating point manner, I will use that one together with my labeling to give me the localization errors, right? Now with these errors, I'm able to plot all the different results, or at least these three results here: the proportion of significant errors, sorted errors, and mean errors. I will also look at I also did a chi-square analysis because it was needed for our experiments to determine, okay, what is an acceptable error, what is not an acceptable error, which errors come from human labeling, which errors are likely due to the method just being flawed, right? To either deep feature encodings being flawed or Lucas-Kanade being flawed. So we need to determine what is that threshold. So that's why we did this chi-square analysis on the errors, because me myself, I can, even though I labeled them right, I could also be mistaken sometimes. Okay, so on the methods, we have decided to compare the following methods: SIFT, SURF with rich descriptors. We have decided to use Lucas-Kanade using a window size of 10 times 10 in a 4-level pyramid, and our methods, which is the deep feature encodings. And then the task is to match the items. So in other words, the nose tip, the face mold, or the hand mold from the first frame to all the other subsequent frames of the video, right? So this part is just to analyze how well does it can it match from the first one to all the other frames. Okay, so then SIFT, SURF, and Lucas-Kanade are converted from RGB to grayscale because that's how they were intended. That's how they were designed. Our deep encodings, we converted from RGB into CLab color space. We converted into this color space because, well, there are four different advantages of using this color space. But the first one, the main one, is that it's perceptually pseudo-uniform. So a large difference in this color space, right? If you compare two colors in this color space, and the difference is large, that means that a human will also consider these two colors to be similar, which is not the case with RGB. A small difference in RGB can be a big difference for a human, and also the other way around, right? A big difference in RGB might not seem very important for us humans, right? So that's why we changed it to the CLab color space. Okay, so we base our algorithm on the assumption that crops that look similar will have similar encodings when passed through the same convolutional neural network, which is the encoding part. So we define the similar pair of crops as the crop that yield the minimum residual sum of square, or the sum of square residuals, which basically is the sum of the representations. So H is the latent space representation of whatever crop I have on my second image, minus the latent space representation of the reference crop, and then I just square that, right? Well, I square that and then I sum it. We aim to build an algorithm that is capable of tracking distinctive phase features, but is also capable of capturing unnoticeable features. Unnoticeable features to us, right? So that's why we use this latent space representation of features, so that we can have a much better space in which we can compare these features and determine whether they are similar or not. Okay, so subpixel level prediction. Okay, in simple words, we perform subpixel level prediction by fitting a surface to the sum of square residuals between the reference point and the point in all the second image and interpolate locally. So I have a reference point, right? And then I can represent that point in a 128 dimensional space. Then I can use this reference representation to compare it to all the other points, right? To all the other points in the next image, right? And then each point then has a sum of square residuals, right? Then I basically the sum of square residual landscape is to put that sum of square residual function as a function of the spatial locations of the pixels in the next image. So then basically and then we want to look at, the idea is that we want to introduce convexity to our algorithm. So we want that if, for example, I have so this is the landscape of the bike video of me, and I'm trying to track a phase mode, right, which is here. This is denoted by this red line, and here we have the local enlargement, the regional enlargement of this point. So a good method will have this very nice mountain, right? Because if it has some little mountain here around that maxima, it means that not only will pick up this point, right? But it will if it at the moment that it didn't pick up this point, it will more than likely pick up the surrounding points, because these are the other points that have the next best value, right? So we let the SSR, so this is quite math heavy. So in simple words, we just let the SSR be this function z, so that this function is then dependent to the x and y position, so the spatial locations of the pixels in the next image. And then we choose a 3x3 window right around that point. And then we look at the SSR of those points. And then we just rewrite this equation so that z is basically the position of those points times some constant, and then we can fit a surface of order 2 to match that the SSR landscape. And then once we have that, then finding the theoretical minimum is quite easy. You just need to find a point where the partial derivative of z and the partial derivative of z with respect to x is equal to 0, and where the partial derivative of z with respect to y is also equal to 0. So you can rewrite that system of equations, and then you end up that the answer is just this, right? This is the once you find your c vector, then finding the theoretical minimum is quite easy. It's just plugging into this equation. Okay, so then chi-square analysis. So a chi-square analysis was used to establish a threshold, as I mentioned before, to determine, okay, which errors are likely to just the labeler being wrong or not being accurate enough, and which of them are due to just the method not being good enough, right? So here we just, for each motion condition, we have 10, we selected 10 images, and then we relabel each image 5 times. And then we computed the errors in the x and y directions, and then that will give us dx dy. And then and we compare all of these errors with the mean of all the relabeling attempts. So that means that our distribution of dx dy is 0 mean. And then the only thing that varies is the standard deviation of this distribution. Now, knowing that we have normal distributions in dx dy and distribution are 0 mean and have a standard deviation of sigma, then we can simulate this chi-square distribution by just sampling stuff from such distributions, right? Some distributions of mean 0 and standard deviation sigma, which is sigma is different from dx and dy. And then that will give us this plot, and where if we just look at the different significance levels, so in here we have a 0.5 significance level, which corresponds to alpha equals 0.5. Then we have these errors, right? So at different significance levels, we have a different error threshold. Typically, so what does this mean? Basically, it means that everything below this significance level is half likely do that a human would do it, right? And more that a machine than the method would do it. So then all the errors, for example, in here is 99% likely that a human would do it, or at least the labeler. In this case, the labeler is me, that I would do this error, and everything above is likely due to the method itself being flawed. Okay, so then deep feature encodings. So we aim to train this autoencoder. So as I mentioned before, well, for those of you who are new to deep learning, an autoencoder is a special type of neural network that uses an unsupervised training strategy to learn the identity function. And what does that mean? So it means that it aims to reconstruct its input. And it can be trained by minimizing the discrepancy or distance between the original data and its reconstruction. It's typically done like this. So you have your input x, then your input x is passed through this encoder subnetwork, which is represented as this function f. Then that's going to give you h. H is the Latin space representation. Then you will get h and pass it through this decoder subnetwork, which is g. And then with that, you're going to get your reconstructed output y. And typically, you aim to minimize the mean square error between these two. Okay, so one just important thing here is that our autoencoder could be thought of as a nonlinear generalization of PCA, principal component analysis. That is because we have introduced nonlinearities, right, through the ReLU functions in the hidden layers. Okay, so what we have here is that we start with a crop that is 31 times 31 times 3, because CLab is also coded in a 3-channel space. Then we apply convolutions, convolution, 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 convolution. until we get to some feature map that is 1 times 1 times 1 times 128. And then we apply transpose convolution. So transpose convolutions basically upsample your feature map, so they make it larger, right? And then they make it larger. So transpose convolutions make it larger, make it larger, make it larger, make it larger, until you have a 31 times 31 times 3 again. That is because you want to have the same input shape in your output as you have for your input, so that you can compare them directly, right? And then just a note that here the input is compressed into a latent space that is about 0.044, the size of the input. So that's a quite large compression. So that means that there's some information that could be lost in this compression. Okay, so how do we get actually to this 128 feature dimensional space? Well, we apply convolutions, 2D convolutions, that are size 7 times 7. So our kernel size is 7 times 7. So each time that we apply the convolution, we decrease the spatial dimensions by 6. So here we have a 31 times 31 times 3. Once we apply this field with this convolutional layer, we decrease the size to 25 times 25 times 16. That is because I have 16 filters here. Then I continue applying another convolution. So 25 minus 6 is 19. So I'm gonna get 19 times 19, and now I have 32 because I have 32 filters here. And then I do that again and again and again until I end up with 1 times 1 times 128. It is worth noting that here I apply the convolution, I apply batch normalization, and then after I apply batch normalization, I apply the nonlinearity. In this case, is ReLU, or rectified linear unit. So why we apply that batch normalization before the nonlinearity? That is because nonlinearity is typically, at least the most famous one, Sigmoid, Tanache, and ReLU. They have some interesting stuff happening at the origin, or the point where the point where we have the 0, 0, and then batch normalization basically allows the network to control the diffusion of our values, right, by allowing it to offset the activations or scale them at the same time, and scale them at the same time. So this is the encoder part of our subnetwork. For the decoder part of our subnetwork, you can imagine that it is the same thing because our autoencoder is symmetrical. So that means that the only difference will be that instead of applying convolutions here, it will be transpose convolutions, and it will be 128, then 64, then 32, then 32, then 16, and then 3. To give us the output shape 31 times 31 times 3. And this architecture yields roughly 1.16 million trainable parameters, which is a decent amount of parameters to train. Okay, so what happens? So let's say I have a video, right, of me, and I want to track stuff on this video. So I will get the first frame, right? And then I will check, I will select something to track. Let's say I want to track my nose tip in this case. And then I would get that nose tip, and I would pass it through my encoder part of my subnetwork of my autoencoder, and then I will get a compressed representation of my nose, right, in this high dimensional feature space. And then on the next frame, I will start getting crops. Like for example, I will get this crop, and then this crop with a stride of 1. So to make sure that I include every possible location of the box in the image. And then I will continue to do that all the way until I get all the possible positions. And then I would pass them again through the same encoder subnetwork to get different compressed representations, right? And the idea is that I want to compare which two representations are the most similar pair, right? In other words, which minimize the sum of square residuals function. And then once I find these two, then I have a match. Okay, so the results. So as you can see, as I mentioned before, our method is the best in almost all situations, and a situation that is not the best, then is still pretty good. You can the plot that I showed in the beginning of the presentation is this plot, but you can see that for all the other conditions, our method is still a good method here will be a line that is very close to these dashed lines, but is below all the other lines. So you can see that our method, the orange line, is always among the lines below, right? So in this method, basically in this situation, uh, it seems that SIFT and SIFT, Lucas-Kanade, and our method perform very well. So this is the one where our method was not the best, where Lucas-Kanade was the best, but you can see that basically the lines are plotted on top of each other because they were all very good. And then this is our method, and this is our method. So this is the tracking the so this one is tracking the nose tip under the bike condition. So in here, yes, our method was a little bit above the threshold line of the 99% confidence interval, but still it was below 10 pixels. I think it's maybe below 8 pixels, as I can see here. All the other methods, they diverge completely, right? So that means that these methods, they wouldn't be good for tracking. Then we have proportion of samples above the threshold as a function of significance level. So if we change the significance level, right, how many samples will fall above that line? So in here, the best methods, basically, the best method is the one who has who is here, right? This corner is the best position of where our methods could be. You can see that everything that is above here is not good, right? Because it has a lot of samples above the threshold at any significance level. For example, SURF basically all the time was having all the errors above the significance level. Then it was SIFT with threshold, SIFT, and our method, this orange line, was always among the ones that were the best performing ones. Here, for example, here was comparable to Lucas-Kanade. Here it was definitely better than Lucas-Kanade. Here was the circumstance where the three methods were the same, in which Lucas-Kanade, as I mentioned before, was the best method, and our method was the third best, and this is reflected here as well. And then in the other one, our method was the best for low significance levels. In other words, high confidence levels. But then, as the significance level grew, then it seems that Lucas-Kanade was a little bit superior than our method. And then okay, so then here we have the distance of the second nearest neighbor as a function of the distance of the nearest neighbor. So here we would like to compare we would like the points to be very close to this line, because that means that the two nearest neighbors are very similar. So like if I didn't pick my nearest neighbor and I picked the second one, would it still be an acceptable solution? That's the question that we're trying to answer here, right? So we want that ratio to be as close to 1 as possible. In other words, to where the y, in other words, lying on the y equals x line. The worst methods are usually above that line, and in here I believe that the size of the marker is proportional to the largest spatial distance of the neighbors to the ground truth. So small circles are good, large circles are bad. So here we can see that we always have very small circles. So I mean at least for the static conditions, we have very small circles. That's because static conditions are usually easier conditions than bike conditions, right? A bike condition is where we have our face moving and probably have a more blurriness and more different stuff that could affect our how the face looks like. And yes, for the bike and nose tip circumstance, we have the largest circles. That means that the second largest nearest neighbor is quite far away from the ground truth, right? And that's not good, definitely. But yeah. So then we have the number of nearest neighbors below the 99% confidence interval. Okay, so so for each condition, we would like to have our line to be as high as possible. This is a sorted. This is sorted. So you can see that, for example, SURF only has a very few ones that are below that are below the 99% confidence interval. Uh, and then SIFT has some of them, but only maybe 2 or 1 in this case, which is not so good. And then we have, for example, 12. So that means that any of these 12, for example, would be a good prediction. Uh, then any of these 25 would be a good prediction. So that means that our method is just much more robust to match objects, to match features from one image to another. And then lastly, we have the sum of square residual for one case. So here is the case that I showed you before, where we have our sum of square residual is very nice. Here we have a little mountain. The other methods is quite messy, right? And you can see that, for example, here this one is at the edge. So yes, here it has a little mountain, but it's at the edge, so it's not very good. And then for surf, it's just like a whole mess. It doesn't. There's no structure to that landscape. Well, for ours, you can see that. Yes, not only does it have a structure here, but the whole landscape is quite good. Like if you look at it, we can see that everything that is skin is highlighted up, which is very good, and that means that it's trying to do some good predictions, right? Because obviously the face mold looks like skin, so it looks much more reasonable structure than the other two methods. Okay, and lastly, if I can go through the conclusions very quickly. Our algorithm is more accurate and precise for feature matching than the traditional computer vision methods for our applications. Many false positives is an inherent problem from calculating the similarity of two high-dimensional feature vectors, because the error can come from any of the dimensions in the high-dimensional space. And then this is the what we attributed our distinctiveness of our feature representations to. So it's the preservation of spatial information, the learning of complex features, and the creation of a set of latent variables that can capture the variance of the samples. Due to the increased precision of our deep feature encodings, we can perform tracking more robustly. That means that when the matching method makes an obviously wrong prediction of the location of the key point, the error is usually extremely large. And this would cause the algorithms to diverge after the instance of the obviously long localization. However, some of the things that we still need to optimize is the computation time, because we still haven't found a way to make it fast enough so that it can be used on real time. Some of the stuff that we're thinking is to use these approximate techniques for matching neighbors and to introduce convexity in the search space. And lastly, current feature tracking and feature matching methods are not yet good enough for the applications that we are interested in. And there is still much work to be done before our pipeline is useful in most situations. However, our deep feature encodings have already shown promising results in terms of precision and accuracy for matching features. And lastly, I would like to thank all of you for listening, and I want to thank all my lab mates for their support and help. And I hope that you keep enjoying this workshop, and I hope to hear from you soon. Thank you so much.
Hello, Jose. Thank you very much for the great talk. I'm the host of the Q&A session. Since we're already in 10 past 3, let me to pick 1 to 2 questions to you from the chat. Is that okay, Jose?
Yeah, sure. That'll be awesome.
So the first question is, great presentation. Could you say more about the application of your methods? What other thing can it be applied?
So, could you tell me who asked that question?
Ame?
Ame? All right. So thank you, Ame, for your question. As I mentioned before, well, let me start by saying our application again. So our application is to track the heart rate remotely, right? Just to looking at the video. The one for the Parkinson one is to we want to quantify the motor function of Parkinson disease patients. So what happens is that right now the way that Parkinson disease patients can determine if they are very sick or not is just through going to the doctor, right? Then they will go to the office, and the physician will um, assess them using the MDS UPDRS score, so the Movement Disorder Society Unified Parkinson Disease Rating Scale, and then it basically basically the subject needs to do different tests, right? Like for example, move their fingers like this, or maybe try to put their hand still and touch their nose like that. But the problem is that that is subjective, right? So it depends a lot on how the subject is feeling that day, and in addition, it also can it depends on how the doctor is, right? If the experienced doctor tends to give different ratings than unexperienced doctor, it depends on the mood of the doctor. So we want to do that more objectively. For more commercial applications, right? You could, as I mentioned before, you could, for example, right now we are feeding faces, right, and skin to the method. So right now it's very good to track stuff on skin. But you could feed it, for example, images of cars, right? And then you will be able to track cars in a freeway, for example. Or let's say you have a drone, and then you want to track where, let's say you are a farmer, and then you have a drone, and then you want to say maybe track where are your horses going or your cows going, right? So you will feed the images of cows, and then you will be able to track cows in a field. There are many different applications for tracking. I think tracking matching is probably one of the most interesting things, most interesting tasks in computer vision right now. Hope that I answered your question. It all depends on your imagination, to be honest. This is just a method, right? And then whatever you use it for is the real magic part. I hope that I answered your question. If not, then please feel free to make a comment still, and we'll get back to it later.
Yeah, thank you very much. I think it's a great explanation. Yes.
Do we have another question?
Thank you very much for your answer. I think it's a great presentation, a great answer. So if the audience have want to say more about that question, please feel free to type in the chat. Yes, we have another question. Let's
All right.
let's have that question be the last one. So that question is, your method looks well performed and robust. Do you think it can be better? What is your plan for improving it?
Yes, I definitely. Who tell me who asked that question?
Well, it's the same person as
Same
previous
person.
one.
All right. Yes. So one of the things that we could improve definitely is on the time that it takes to run this method. Definitely, the method is. I wouldn't call it fast. I would actually call it very slow. Because right now we're just looking at when we're doing the experiments, we're looking at feature matching ability. Now there are several tricks that we can apply to the method so that we can get an approximate solution, and we can get like a faster matching between the images. That's not a big problem, but the main thing is the computation time. Now in terms of accuracy, the thing is that accuracy is a little bit hard for us to find a way to improve it, because as you can see, in a lot of situations, our method has the same error as SIFT and SURF. And the problem is because I think the main problem is because it was only one person labeling, right? So one thing that we could improve, so that the error is just based on me, right, on my labeling. If we have, for example, a consensus labeling, like let's say we have 3 people labeling the same image, then it will be much better, because as you can see, it's not the same thing. I mean, accurately pinpointing where is a nose tip on an image is a task that even for a human you can detect it with 100% accuracy all the time, right? I mean, if it's not the same task as, for example, if you show me a picture and you tell me, is this a dog or a cat? I could tell you a lot of the times the correct answer, right? Or a boy or a girl, right? Is I will be able to tell you 99.99999% of the time the correct answer. But in this case, because it's like pinpointed the location, right? In an image is you always have like maybe like 2 or 3 and that's why we did this chi-square analysis, right? To be able to understand that yes, the labeling is not perfect, obviously, but we want to still use this labeling to determine, okay, what is likely due to what error is likely due to me labeling, and what errors is likely due to just the method not being good enough, right? Like for example, if the method has an error of 3, okay, you could tell like, oh, is it 3 because it's just the label is wrong or something. But if the method has an error of 100, then you know that the method is obviously not good, right? It will be tracking, instead of this one, it will be tracking some stuff elsewhere, right? That is obviously wrong. And we want to look at those errors, right? We want to minimize those errors.
Yes, thank you very much for the answer. So this is the end of today's workshop. We will have another hackathon at 4 p.m. the same day today. So just like 14 minutes later. For more information, please check our website. We have put the link in the chat, so you can just click it. Look forward to seeing all of you. Thank you, everyone. Thank you, Jose.
Thank you.